record. So, I think I've maybe resolved most of the Learning Suite issues. Now you should be able to go in and see your answers, what the correct answers are for exam 1, and for most of the questions, at least for the multiple choice ones, not matching, but multiple choice ones, you should be able to see a video explanation for the question. For some reason, Learning Suite coding does not support feedback videos for matching questions. They've actually never had anybody paste a video in for feedback on Learning Suite before. So we're breaking some new computer science ground in this class. In any case, if you have concerns about how you did on the exam, start by watching the Exam 1 advice video on my YouTube channel, and then watch the videos for each question. If you have questions and want to meet one-on-one, I've sent out a link to a Google Sheet. It is now, should be possible to edit by everyone. Be good humans and don't replace each other's names in the time slots. No stealing time slots, whatnot. I've got sort of roughly 10-minute slots from tomorrow through Friday. If you want to take up all my time between now and then, you are welcome to do that. The meetings will be via Zoom, I think is probably most convenient. But don't feel obligated. You don't have to come talk to me, but you are welcome to do so. The Google Sheet is for signing up for a one-on-one time to meet about the exam. That question about the video for number 22 isn't working. Has it worked for anybody else? Don't know. I'll look into that. I'm trying to figure out a way to share feedback videos with you guys without having them all over the internet, so I have to write a whole new exam every time I think about an exam. So if anybody knows how to share videos privately without me having to enter in 400 different email addresses one by one, if anybody's got some knowledge there, that would be useful. Okay, I think that's it for housekeeping items. So we left you last time with a fun little problem. We decided to change up the butane conformations by adding another molecule, or another atom rather, to the carbon in the back. And we found that there were 3 different staggered conformations now and 3 different eclipse conformations. And I wanted you to think about which ones, whether there was any difference between the staggered and eclipse conformations. And if you had to pick, is there one you would think of as more stable? So let's just start with the staggered conformations. What do you think? What differences do you see? Which one do you think would be better than the others? Is there a rank order? Go ahead.
I think first off, on the third one, you can cut that one out as like the lowest energy because all of the big groups are right next to each other.
All right. So the comment here in class was that for staggered conformation 3, you have 2 gauche interactions. You have a methyl to methyl gauche interaction, and then you have also a methyl to hydroxyl gauche interaction. We don't have to really count the number of times protons are gauche to each other or other things because there's simply no other options than that. All right, so you see that as worse than the other available options. And I agree with you. So what about staggered 1 versus staggered 2? In staggered 1, we have the 2 methyl groups gauche to each other. In staggered 2, we have a methyl group gauche to a hydroxyl group. I guess if we want to be complete, we could say that methyl and hydroxy are anti to each other in staggered 1. Whereas methyl and methyl are anti to each other in staggered 2. Any other differences you see? Okay, so which of these options, staggered 1 versus staggered 2, is less bad? Okay, 1, 2?
2.
More the votes for 2, okay. I agree with 2, but justify it. Why?
The hydroxy group is smaller.
Hydroxy group is smaller. Okay. How do you know that?
2 atoms, which is 3.
Okay, well, you can think of the shape. So a methyl group looks like that. A hydroxy group looks like that. So there's just fewer atoms, right? And you can probably twist around this bond to get this hydrogen out of the way. Okay. And I agree with you, that's right. There's actually a quantitative way that we can sort of tell how big things are, and these are the so-called A values that are in the study guide. For right now, you can just think of them as somewhat as an assessment really of size. It's not exactly that, and I will tell you where the values come from. But for example, squiggly line here means whatever the hydroxy group is attached to. That has an A value of 1. These are actually in kilocalories per mole. You may wonder, what does energy have to do with size? Stay tuned, we'll get to that at the lecture. Fluoro is really small. These are all relative to hydrogen, by the way. So the A value for hydrogen would be equal to 0. So fluoro is pretty close to, and these aren't numbers to memorize, just sort of trends. And then methyl is like 1.7 kcal per mole. And so just based on those numbers, yeah, okay, a methyl group is bigger than a hydroxy group, and so you're pretty confident in concluding that if we were to rank these, staggered 2 is going to be our most stable. Staggered 3 is going to be our least stable. So I suppose if we want to make an energy diagram, let's go ahead and drag staggered 2 down a little bit. Who knows how far? We may not know. It's fine. Staggered 1's a little bit higher, and then staggered 3 would be higher than that. All right. Eclipse conformations we can rank using the same sort of reasoning. So which one of these is worst? Three, methyl eclipsed with methyl. All right, just based on those size configurations or arguments. Hydroxy versus methyl, and methyl versus hydrogen for eclipse 2, and then for eclipsed 1, everything is eclipsed with hydrogens instead of with each other. So that's probably the best of your available bad options. So again, I don't actually know what these energies are. It doesn't really matter what the absolute energies are. What's useful is for you to be able to rank them in order of goodness / badness. And one of the interesting things here is that it doesn't necessarily, the rank ordering of eclipse conformations doesn't necessarily track with the rank ordering of staggered conformations. All right, so yes, the question is, do you really want to, is the principle you want to keep the biggest stuff furthest apart? And the answer is yes, though if we introduce another non-hydrogen group on this molecule, the rules are going to start to change for reasons that aren't important and are that I only just barely learned about when I taught that advanced OChem class. So yes, for our purposes, you want to keep the biggest stuff furthest apart from each other. All right. And yeah, the A value is basically a quantitative assessment of how bad it is to have big stuff close to each other. All right, any other questions about butane conformations? All right. So now we need to talk about cycloalkanes. And this is fun because we get to draw shapes. When my kids were little, when I was going to grad school in Wisconsin, we'd go up to my mom and dad's house. They lived in the Fox Valley, a little town called Neenah. Go Packers. We were transplants, so we really didn't understand the religious devotion to the Packers that people who are from Wisconsin. I almost said Wisconsin because that's how they say it there. Anyway, we go up to my mom and dad's house, and they had this little toy for my boys, and you would hit it, and it would say something about shapes, colors, animals, and then it would continue playing, and you didn't have to jostle it very much before it started up again, and it was so obnoxious, and my kids loved to hit that thing and have it continue to say shapes. So every time I say the word shapes, my mind repeats colors, animals, again and again. In fact, this toy still exists at my mom's house. They've moved here, and if I want to, I can go over and hear that again, and it's still, there's no nostalgia. I still hate that thing, so. All right. Somebody asks, when does hydrogen bonding interfere with energy differences between having something gauche and anti? I can give you an example of that just briefly. This derails us from cycloalkanes, but it's fine. You might think, well, what if I had a molecule like this? This is actually antifreeze, ethylene glycol. What if I had this molecule? How stable is the staggered conformation versus something else? And it turns out that there are some orbital arguments for the gauche conformation being better than the anti-conformation. But another potential argument is, I don't know what in the heck I'm doing here. Sorry. The other potential argument is that if the two hydroxy groups are gauche to each other, maybe I won't draw that hydrogen in the back. If the two hydroxy groups are gauche to each other, one can sometimes hydrogen bond with the other. So there are situations where gauche can be more stable. I don't see myself asking you about them again. That's a chemistry 552 kind of question. All right, cycloalkanes. Somebody wants to know, do we need to know the energy diagram of the 6 conformations relative to each other? If I draw you a molecule and I say, which is the most stable staggered conformation of this molecule, then yes, you better be able to figure it out. I suppose I could also ask, which is the least stable eclipsed conformation? I guess that would be a different way of asking the same sort of question. All right, cycloalkanes. So if you look at the friendly neighborhood equilateral triangle, geometry class, what is the interior angle of an equilateral triangle? 60. There's an equation, and I forget how it was derived or what it is. So, and as with most things I don't know, I also don't care. So there you go. All right. So if the angle's got to be 60, then what about cyclopropane? We'll just draw that. Each of those carbons is attached to 4 different things. So you would think ideally each carbon would be sp3 hybridized, tetrahedral. All right. Fine, but if that's the case, then what should the bond angles be for an sp3 hybridized carbon? 109, that's the sort of magic number. 109.5 if we want to have more significant figures. But the idea is that in cyclopropane, you can't have the ideal bond angles. And that requires some distortion, and the difference between ideal and reality is called strain. And frankly, this is probably true in mortality in general. The difference between what you think is ideal and the way your life really is can sometimes cause strain and stress. Well, it's the same for cyclohexane rings. Trying to see. We'll draw a cyclopropane ring in the Spartan app. And cyclopropane, don't get the wrong idea, cyclopropane still exists. But if you calculate the heat of formation for this molecule and compare it to the heat of formation for an analogous molecule with exactly the same kind of bonds but no strain, there's a sizable amount of strain energy. And we will see in a few cases later this semester, we will have three-membered ring containing compounds as intermediates in a reaction, and sometimes opening that ring up can be favorable. Cyclohexane exists and is decently stable. It has a way of getting around the strain. There's a fun orbital explanation for how all of this works that, again, probably is beyond the scope of this class. I'll give you a little hint. Think of each of those carbons in cyclopropane as actually being sp3 hybridized, but on its side. You don't have to worry about that. That's just a little aside. But if you need something to ponder while falling asleep, you could ponder that. So you've got ring strain or angle strain, and this is adding to our list of strain or things about shape that can make some molecules more stable than others. Cyclobutane, again, you see a required 90-degree angle if the square were going to be perfectly flat. Now, for cyclopropane, 3 points define a plane, so there's simply no other way to arrange things. There's no way to get around the angle strain. But for cyclobutane, there is a way. All right, so imagine again, ideal bond angle is 109.5. If it were flat, reality would be 90 degrees. And so, someone's asking, what is the difference between ring strain and angle strain? I guess we can use this interchangeably. Is there an E in interchangeably? Who knows? Another thing I don't care about. So what will happen, I'm going to try to draw this molecule from the side. If we were to constrain that ring to be flat, you've got angle strain here because this angle isn't ideally 90 degrees. But then if you were to look down this carbon-carbon bond between carbons 1 and 2, what you would see is that all the bonds in the front on carbon 1 are eclipsed with all of the bonds in the back on carbon 2. So with flat cyclobutane, not only do you have angle strain, but you also have torsional strain. So what happens? Well, the ring puckers. What do we mean by that? That's kind of dumb and we need a better word for it. But basically, the ring is going to relax so that the carbons in pink are going to raise themselves upward and the carbons in blue are going to push themselves downward to have a more relaxed shape oops, it's kind of hard to draw. Where you got hydrogens on the ends that are pointing straight downward, and in the middle, hydrogens that are pointing straight upward. And in this way, the angles more closely approximate 109.5. And you also relieve some torsional strain because you're not, I'm sorry about the penmanship here, because you're not entirely eclipsed. Eclipsed? Can't spell. Eclipsed. All right. So let me give you an example of this in the Spartan program. We'll erase our triangle, and now we get to draw a square. Except that's not a square. That's also not a square or even a parallelogram. All right, so here is the cyclobutane molecule, and we're going to zoom in on it, and can you see that it is not completely flat? This should resemble the way that I drew the molecule on paper. You have carbons on either end, where you've got hydrogens pointing sort of down, and then carbons in the middle where you've got hydrogens pointing directly up. This is the puckered form of cyclobutane. And probably this thing is flapping around like a bat, changing from one puckered form to another. The two carbons on the end are down / up, flapping back and forth. And if you look down a carbon-carbon bond, you can see that we're not perfectly staggered, but we're also not completely eclipsed. So this happens to be the best that our poor friend cyclobutane can do. If you were to actually measure these bond angles in this shape, they're closer to 109.5. They're not quite 90. And you have relieved some of the torsional strain. So we would say that cyclobutane is less strained than cyclopropane on an atom-for-atom basis. Could you say, someone asks, are the middle carbons eclipsed with each other? Well, remember, I suppose it looks like they're lined up with each other, and so I suppose you could, though we are reserving the term eclipsed and staggered for two carbon atoms that are bonded directly to each other through a sigma bond. And as those two middle carbons are not bonded to each other, it's probably not a big deal that they're eclipsed with each other across the ring. All right. So four-membered rings are found in lots of organic molecules. In fact, if you have ever taken a beta-lactam antibiotic, like, say, penicillin or amoxicillin, you have ingested a molecule that has a four-membered ring. So beta-lactam. My son was attempting to email people. Hello, ADDAM. His name is Adam, and a friend spells his name that way. It's kind of fun. See the four-membered ring there in the beta-lactam antibiotic. It turns out that opening of that ring and relieving the ring strain is an important part of how that antibiotic works. All right. Question so far? Yeah.
So is it true that cyclopentane would be less strained than
Yep. Absolutely. Yeah, so cyclopentane now, and I forget, as I said, I forget what the formula is. I think the internal angles for, something says to me the internal angles for cyclopentane should be, I don't know. Does anybody know? Yeah, go ahead.
What's the type of strain that's relieved when the butane is bent like that a little bit?
The angle strain and the torsional strain.
Okay, so both those are
that
Yep.
more, the bigger the ring, then the more, or the less strain you have?
That's right. Well, not, okay. To a point, actually, it turns out that once you start getting larger ring sizes, it all has to do with this comparison of what the ideal angle would be in, say, a hexagon or an octagon or so on, with what with what the preference for sp3 hybridized carbon is. In general, chemists have observed that ring sizes sort of from 5 to 7 are pretty good. 8 is fine too. There are larger rings, but there are some weird issues that start to crop up with larger rings that we don't need to do or worry about. But yeah, ring puckering relieves angle strain. So you can think of cyclobutane as being kind of stressed and full of angst. And relieved now because of the puckering. For 5-membered ring, strain is even less. So, and we don't, 5-membered ring conformations are a little bit difficult to draw. The way that the ring tends to pucker is you have these 4 atoms are not in the same plane. One is sort of going straight, the other sort of going up, and then the third is angled downward. And you have, so it's almost like the puckered conformation for butane, only in the back you've got 2 carbons instead of just 1. And do you need to know how to draw that? No. Sometimes people call this an envelope type conformation. Again, your guess is as good as mine. I suppose if you think about these 4 carbons as being the square or rectangle part of the envelope and this being the flap, I don't know. But ring strain is a little bit better in cyclopentane, and I'll show you an example of that. And cyclopentanes are all over the place in natural products and in organic chemistry. I wish I knew off the top of my head what the preferred bond angle was. I'm kind of embarrassed that I don't. But here is that puckered conformation in sort of the orientation that I drew it for you. You've got the 4 atoms that are sort of lined up, and then 1 that's sort of lower. 5-membered rings are all over the place in your nucleic acids. The ribose ring is a 5-membered ring. You just replace one of those CH2 groups with an oxygen. And there have been a lot of studies as to what the preferred conformations for those ribose rings are. But yeah, you'll see these all over. Okay? So the one that we have the most experience with, oh, somebody points out, thank you, the flat pentagon interior angle should be 144. So yeah, it wants to be even. Now it's not a question of getting smaller, it's a question of wanting to distort beyond what 109.5 is. Okay. So lastly, let's talk about hexagons. Internal angle wants to be 120 versus 109.5. And the 6-membered ring is magical because by puckering, it can adopt a conformation that has no angle strain and no torsional strain. Why is it bad to have a bond angle larger than 109.5? Wouldn't strain be lessened because they are further apart? That's a great question, and it's tough to answer. If you were to make a model of a molecule and try to have a carbon that was sp3 hybridized and then try to stretch the bonds on that sp3 hybridized carbon to be wider, you would be distorting it from its natural shape. In the end, what it has to probably do with is optimal. Oh, we're getting bad information here and there. Somebody calculated 144. The actual number is 108. And I'm embarrassed that I'm just leaving this to crowdsourcing. I'm sorry. I have it in my notes somewhere. I just didn't want to look it up. So my apologies. Someone asked follow-up question. 108 is pretty close to 109. Why pucker? And the answer for why cyclohexane puckers is, again, look at those down the carbon-carbon bonds. We're relieving torsional strain by puckering. In any of the flat conformations, if you look down the carbon-carbon bond, you've got eclipsed interactions. Puckering relieves that. Go ahead.
For pentagon rings, isn't that only one of the carbons that should be puckering down there?
Yeah, for the pentagon ring, it's a little bit more than that. It looks like, so if we look at it from this perspective, it looks like one of the carbons is puckered down. The two bonds, the one in front and the one in back, aren't exactly parallel, so it's a little more complicated than that, but in effect, you can think of it that way. And you'll notice that not all of the bonds have totally relieved angle strain. There's one there that's still pretty close to eclipsed. Yeah?
Does the way that it puckers, is it affected by the molecule or the atom that's attached to the carbon?
Is the extent of puckering influenced by what atoms are attached to the ring? Certainly. And the story is pretty complicated for cyclopentane rings. It's a lot simpler for cyclohexane rings, actually. But yeah, putting groups that are not hydrogen on these carbons can influence the conformations. All right, sorry about the bad information. We're beta testing this lecture right now. So with cyclohexane, you can relieve angle strain because once you pucker, all the angles are 109.5. And there's no torsional strain because all the dihedral angles, bond angles are 109.5 and all dihedral angles are staggered. Someone has asked, so angle strain has to do with bond angles and torsional strain has to do with dihedral angles? Yes, that's right. So the conformation is called the chair. And I will show it to you in in Spartan, and then we will learn how to draw it. And then we'll talk about the options that are available to the chair. Oops. All right, so here is your lovely cyclohexane ring. Notice that the cyclohexane ring is not flat. If we look at our cyclohexane ring from above, we can see that there are 3 hydrogens pointing directly up at us. I wish Spartan had a pointer function, but it doesn't. Save. Okay, whatever. We've got 3 carbon-hydrogen bonds pointing out toward us. And then on the other 3 carbons, we have carbon-hydrogen bonds that are angled upward but splayed out. Okay? The protons that are angled directly up toward us when looking down from above, we are going to call axial, because if we imagine that this cyclohexane ring is the belt around the Earth, the axial protons are pointed up along parallel to the axis up to the North Pole and the South Pole. And the protons that are splayed outward we're going to call equatorial, because they are sort of aligned along the equator. Notice that the 3 protons that are axial, that are pointing upward, you have 3 protons that are axial upward and 3 protons that are axial downward. Similarly, you have 3 protons that are equatorial upward and 3 protons that are equatorial downward. Now, if we look down the carbon-carbon bonds, say this one, for example, notice that that's a staggered conformation. So there's no no torsional strain there. And if we look down the rest of the carbon-carbon bonds one by one, we'll see that they are all staggered. And this is why cyclohexane has no torsional strain. Moreover, if you look at the shape of this molecule, you can see that each carbon looks like it is tetrahedral, and indeed it is. The bond angles in chair cyclohexane are 109.5 or so. So it just so happens that 6 tetrahedrons arranged in this pattern, there's no distortion needed. All right. What questions do you have about cyclohexane? Spinning it around, kind of boring. So every other carbon goes up like a zigzag? Yes. So let's talk about how to draw chair cyclohexane. This is a hard part. This is where you feel like it's more of an art class than a chemistry class, and I'm sorry. You should get good at drawing chairs and interpreting chairs. Now, of course, on a multiple choice exam, I'm not going to be evaluating or laughing at the quality of your chair drawings. However, drawing a good chair will be very useful in answering a lot of questions, particularly when we get to Chapter 8. So, here is a 6-membered ring from the top, and each has a carbon-hydrogen bond, one pointing up at us and the other pointing downward. I'm going to number the atoms 1, 2, 3, 4, 5, and 6. And we will start with atom 1 up in the corner. And we're going to draw a line from atom 1 to atom 6, sort of at a diagonal. And then we're going to imagine on carbon 1, we're going to fill in the hydrogens that are implied but not shown. Let's see. We'll also draw the bond to carbon 2. On atom 1, we'll have a proton that's up and then a proton that's down and equatorial. So this proton is up axial, and this proton is down equatorial. In the way we're drawing this molecule, we're going to say that carbon 1 is an up carbon. All right, so we're looking at the molecule. Our perspective in drawing the chair is really from that angle. All right? So once you've drawn that first tetrahedron, you've got the tools to draw everything else. When we draw the bond from 2 to 3, we are going to make it parallel to that carbon-hydrogen bond. Okay, so each bond is going to be parallel to the bond that's one bond away. So here's carbon 3. Similarly, as we draw the line from carbon 6 to carbon 5, it's going to be parallel also to the bond between carbon 1 and its down equatorial proton. See how those are parallel? All right, what do we do about carbon 3 to carbon 4? This bond is going to be parallel to the line between 1 and 6 across the ring. And then we just complete the six-membered ring by connecting atoms 5 and 4. So to keep yourself from, to orient yourself so that you're drawing the chair correctly, the bonds between 5, oops, I didn't want to erase, I wanted to highlight, 5 and 6 is parallel to the line between 2 and 3, and also parallel to the line between 1 and its down proton. Similarly, what else to do? The line between 1 and 6 is parallel to the line between 3 and 4. Okay, so carbon-carbon bonds are parallel to the ones directly across the ring in this drawing. And we're looking at the molecule sort of from this angle where we've twisted the molecule downward. Carbon 1 is up there in the back. Yeah.
Why is it called a chair confirmation?
Yeah, why is it called a chair conformation? Because if you take the chair shape and you turn it on its side a little bit, and then you twist and add a few embellishments, you can imagine that this is a Adirondack chair. I'm sorry, I didn't make it up. The bow tie, I suppose, would also be appropriate. I don't know. Okay, so a couple of features about a chair that are interesting. We've talked about things that are parallel. We've talked about how carbon 1 was an up carbon. So are carbons 3 and 5. All right. In contrast, carbons 2, 6, and 4 are down carbons. And oops. All right, let's talk about up carbons. For up carbons, the protons that are up are axial. Up carbons have up axial protons and down equatorial protons. Notice on all 3 of these purple up carbons, you've got axial up protons and equatorial down protons. Where to draw the carbon-hydrogen bonds? For carbon-hydrogen bonds, you try to draw them parallel to the carbon-carbon bonds that are one bond away. So the bond in the front between 5 and its proton is going to be parallel to the blue highlighted bonds there. Similarly, the orange highlighted carbon-hydrogen bond is parallel to the orange highlighted bonds, carbon-carbon bonds. All right? So on up carbons, the up proton is axial, the down proton is equatorial, and we'll just switch that for the down carbons on carbons 2, 4, and 6. Down carbons have down axial protons and up equatorial protons. For the bonds between 4 and its proton and 6 and its proton, we're again going to try to be parallel to the bonds that are one bond away. Okay, so that's the slow story of how to draw the chair. Questions about this? Someone is asking, where do we find the Google Sheet to meet about the exam? It is in the Learning Suite announcements. All right, so that's sort of boring. What happens when we put a substituent on the cyclohexane or the cyclohexane ring? What if we replace one of those hydrogens with something else? So let's just make it, I don't know, let's just make it a hydroxy group for now. Let's have the OH be up on carbon 1. So I'm going to take my chair drawing that I just barely drew, and I'm going to look and start numbering. I'll draw the chair, and then I'll start numbering around the ring. It doesn't matter where I start. I could start with carbon 1 being an up carbon, or I could start with carbon 1 being a down carbon. That may not make sense, but hang on. Then, and I've got to make sure I number around the ring, both rings in the same direction. So 1, 2, 3, 4, 5, 6 in a clockwise sense. I would go clockwise here. Doesn't matter for this example, but it will matter for other ones that are more complicated. At carbon 1, as I've drawn the chair, 1 is an up carbon. So there should be an up axial and a down equatorial position. Where should my OH group go and where should the proton go?
Up.
OH goes up, proton should go down. All right, see that? And you don't have to fill in the other carbon-hydrogen bonds if you don't want to. If you want to practice, it can be good. Sometimes people struggle with how to draw the carbon-hydrogen bonds in the back. Again, follow the parallel rule. This carbon-hydrogen bond we just draw is an up equatorial carbon-hydrogen bond. Now, go ahead.
How do you know that the hydroxyl group is up there and not equatorial?
So how do you know that it's up and not axial and not equatorial? We know that it's up just based on how we drew this. We know that it's up axial because I chose to put carbon 1 at an up carbon. Now let's see if I chose to put carbon 1 at a down carbon. Let's instead put carbon 1, 2, 3, 4, 5, and 6 here. At down carbon 1, the up position is actually equatorial. Right? So a reasonable question is, well, how do you know which one to do? And you don't. And in fact, you have to consider both of them because they are in equilibrium with each other. And you could ask, what is the equilibrium constant? You can interchange from one chair to another. And there's not a really great way to show you how to do this in class other than for me to bring a model set, though that could be challenging for the folks at home to see. So let's just talk briefly about what happens when one chair converts to another. And we call this ring flipping. In ring flipping, the up carbon becomes a down carbon. So you got to imagine taking your molecular tweezers, grabbing hold of that carbon 1 and twisting it downward instead of upward. And the two carbons bonded to carbon 1 make adjustments to accommodate that. And then you take the carbon across from carbon 1, which is carbon 4, and you grab your tweezers and you grab that carbon and you twist it upward. and then carbons 3 and 5 that were bonded to 4 have to adjust to make accommodations. As an example, notice that carbons 1, 3, and 5 are up in the chair on the left, but carbons 1, 3, and 5 are down in the chair on the right. So chair flipping involves all the up carbons becoming down and all the down carbons becoming up. I'll try to come up with a better way of illustrating that ring flipping next time, and we'll leave it there. Chapter 4 still not going to be due tomorrow, probably Thursday.